Okay, so hello everyone. Welcome to a new MIST seminar. So this one is actually the last of 2022, so we will have a break until the new year. And we are actually very pleased to have Ingrid Cnossen today with us. She's coming from the British Antarctic Survey and is an independent research fellow there. And she's going to talk today about the climate of the upper atmosphere at Earth with long-term changes in the north-south asymmetries. So yeah, when you want, Ingrid, the floor is yours.
Okay, thank you very much. Yes, so I'll be talking about, most of the talk is actually about long-term changes in the upper atmosphere, and then towards the end I've got a little bit about north-south asymmetries as well, because they are in some ways linked to the same kind of processes that are responsible for long-term changes as well. So I wanted to talk a little bit about this figure here to start with. This gives a very quick overview of the global picture of long-term change actually throughout the atmosphere. So we have the typical temperature profile here with warming in the troposphere and cooling in the stratosphere and mesosphere. In the upper mesosphere, lower thermosphere region, it's a bit complicated, and that's partly because as the entire middle and upper atmosphere are kind of cooling, the temperature structure is moving down. The whole middle and upper atmosphere is contracting, and that movement of the temperature structure makes it kind of hard to quantify changes here. It might also be that there's just not that much change going on, but locally you might see either a positive trend or a negative trend or nothing at all. And then in the lower thermosphere, because of that contraction and the downward movement of this entire temperature profile, we tend to see a local warming trend as long as you look at a fixed height reference frame. And then at higher altitudes, you typically see increasing trends with altitude. And those changes in the temperature structure of the atmosphere also have further consequences for thermosphere density for one thing, but also for the electron density. So this is a kind of typical profile of electron density. And as the atmosphere contracts and layers are lowered, you can see that also in the ionosphere, especially in the E layer and the F1 layer. You can see a downward movement and an increase in electron density because of this positive gradient in the electron density. In the F2 layer, it becomes a bit more complicated because, again, you get different trends depending on what location you're in. And that's probably because the F2 peak parameters are also affected by other processes that have nothing to do with this kind of global contraction and global cooling that we see in the global average. Okay, so okay, I was expecting to advance the slide here, but it's not working. Let's try it this way. Okay, I hope you can see that. So yeah, I wanted to talk a little bit about the relevance of upper atmosphere climate and climate change. So basically the why do we care bit. And there's several reasons for that, but probably the most important reason is that the long-term decline in thermosphere density, which is related to that atmospheric contraction as the upper atmosphere cools, that increases the lifetime of space debris. And because space debris remains in orbit for longer, it builds up faster. It has an impact on the likelihood of collisions with active spacecraft, but also with other pieces of debris. And it might need to be taken into account also for long-term mission planning, this change in atmospheric drag. So what we see here, this figure shows how the density has been changing over time. This is data from lots of different objects in near Earth space that are orbiting near Earth space, and the analysis of their orbital characteristics tells you something about the density. And you see that there's a lot of shorter term variation in there, very strong solar cycle signal as well. And then on top of that is this red line, which is a decrease in atmospheric density. I should also point out this deep solar minimum here in 2008, 2009, which is resulting in especially low densities that are not really related to the overall long-term density trend. But even without that really deep solar minimum, you would see a reduction, a long-term reduction in thermosphere density. And if we're looking at what that means for the space debris environment, this is a plot from the thesis of Matthew Brown, a student I worked with. He's now in Birmingham. He completed last year. And he looked at different scenarios for how the CO2 concentration could evolve into the future based on the same kind of scenarios that the lower atmosphere modeling community also uses to assess the impacts of climate change on the atmosphere. And so if we are looking at, this is all relative to the year 2000, so if nothing changed with respect to the year 2000, then you wouldn't see an increase in the number of trackable objects, which is what's plotted here. But even the most optimistic scenario, so RCP 2.6, would result in an increase of about 40% of the number of trackable objects in near Earth space. And if you have more pessimistic scenarios, then that obviously gets worse. So that is an important reason to care about upper atmosphere climate change. Some other reasons are that also ionospheric changes can have some impacts. So for instance, sea level measurements need to be corrected for ionospheric effects, as they rely on signals that propagate through the ionosphere. And if you have a long-term change in the ionosphere, you obviously don't want that to end up in your data product. So that's something to be mindful of. And with a question mark, I've got here also potentially long-term changes in space weather, by which I mean that if the background ionosphere, thermosphere changes, potentially it could respond differently to the same kind of disturbance coming from the solar wind magnetosphere system. We don't really know about that yet. We haven't really looked into this much yet, but I think it's a relevant question as well, and we should investigate whether that could be the case, because that could be important too. So let's talk about some of the key drivers of upper atmosphere climate change. So we talked a little bit about solar activity variations already. You could see that in the thermosphere density records very clearly. So it's here shown as the F10.7A index. That's the 81-day average of the F10.7 index, which gives a good measure of the EUV radiation coming from the sun, which is important for the upper atmosphere. And also geomagnetic activity here indicated by the KP index has a clear impact on the upper atmosphere that you can usually see back in observational records. But usually for long-term trend purposes, we want to filter out these effects because we're not really interested in solar cycle variations. It's more about the longer term variations. So typically these variations are being filtered out. And what's left then is mainly two factors. So one is the increase in CO2 concentration that is responsible for a lot of the cooling of the upper atmosphere. So CO2 cools the upper atmosphere because most of the radiation that is absorbed by CO2 is re-emitted out into space. So it actually gets rid of energy, and so it cools the upper atmosphere and the middle atmosphere as well, resulting in thermal contraction, as I mentioned. And there's also a possibility that these changes in the climate in the lower atmosphere introduced by increases in CO2 concentration could ultimately affect the upper atmosphere through indirect dynamical pathways. So for instance, there are some indications that gravity wave generation processes and gravity wave propagation characteristics could change throughout the lower and middle atmosphere as the climate is changing. Unfortunately, we don't really know yet what that means for the upper atmosphere, because these effects are very difficult to characterize in global models. We don't really have a very good handle yet on how the long-term changes, or even the current state of gravity wave activity affects the upper atmosphere. So that is still another thing with a question mark, an open question on how important that might be. And then the other important effects for long-term change in the upper atmosphere, which is what I've worked on the most, I would say, and this is what most of the rest of the talk will be about, is magnetic field changes. So the figure here shows the magnetic field strength in 1950. The different colors indicate the field strength. You see also the location of the magnetic equator plotted here by the white line, and the white dots here are the magnetic poles. And then this is the difference between 2015 and 1950. So you see a northwestward movement of the magnetic poles and also of the magnetic equator, especially in this region here. And this is also roughly the region where the magnetic field strength has increased most. So I call this the Atlantic region. It's kind of this general region of mostly the middle and southern part of the Atlantic Ocean, most of South America, and some parts of Africa. And that is to do with a change in the region here, which is known as the South Atlantic Anomaly region. It's a region of a relatively weak magnetic field strength that has been deepening over time and expanding over time, and is still doing that, and also moving in a kind of northwestward direction. So that is where we expect the strongest changes, strongest effects of magnetic field changes. So that is a very important feature of these magnetic field related effects. They are regionally varying. We don't expect them to be the same everywhere. And they are most directly important for the ionosphere, because of course the charged particles respond most directly to magnetic field changes, but there are also some effects on the neutral upper atmosphere, as we shall see. So I decided that I was going to do a long transient simulation with Wacom-X, with all of these drivers included that I just talked about. And I wanted to do this because previously most of the work on long-term trends in the upper atmosphere relied on snapshot simulations with models where maybe a simulation would be done for the CO2 concentration in 1960, say, and then another one for 2010. And then you look at the difference between those two and say, okay, over these 50 years, this is what changed, and this is what the effect of the change in CO2 concentration was. But you're missing realistic solar cycle variations. You might have, you might want to do a comparison with an observational data series, but it happens to be starting in, say, 1974 and ending in 2003 or something. And, you know, you can't really match what you see in the observations, and you have to make quite a lot of assumptions to do reasonable comparisons. And I thought this is a nice way to try and do something that is that produces a data record that is more comparable to observational data records, and that you would be able to compare more directly. And the data is freely available as well. It's in a repository, so anyone can use that. I used it to look at long-term trends in a number of parameters. First, we'll look at some global means. I just used a very simple linear regression analysis, but I did look at different kinds of regression models. So the first one is a very simple model with just a constant, and then a term for solar activity, and then a trend term. And then for the second model, I added in a geomagnetic activity term. And then for the third model, I added in also an F10.7a squared term, so a squared solar activity term. And then I looked at temperature trends and density trends. Both of these are at 400 kilometers altitude. And what is plotted here is the trend as a function of the end year of the data record. So in every case, I started analyzing trends from with data from the year 1950 as the starting point, but ending the time series at different points, just to see if I get a similar sort of trend, because that's really what you would expect if you've removed solar and geomagnetic activity variations appropriately. At most, you might expect that maybe trend magnitudes increase slightly over time, because if they are mainly due to the increase in CO2 concentration, then because the CO2 concentration has been increasing more rapidly over time, you might see somewhat of an increase in temperature trends and density trends over time, perhaps. But what we do see is for the temperature, there are these large fluctuations, which kind of suggests that there could still be a bit of a solar cycle signal remaining in the data. And it's difficult to really pin down what is the appropriate trend value to quote in this case. There could also be an influence of this deep solar minimum here of 2008 to 2009, which skews these trends to be more negative perhaps than they ought to be, because it might be that the linear regression model just can't really handle that very well. For looking at the densities, then the third model actually does a much better job of keeping these trends relatively stable, and you get a better idea of that, that this sort of trend of around -3% per decade or so is a reasonable estimate of the density trend that's in the model data. But just the fact that we struggle so much to get an accurate trend for the temperature tells you how difficult it is to do this based on observational data, where you often have not as much data as I have available here for 66 years worth of data. I've got no data gaps at all. You rarely get that with observational data records, and so you could see that it is really hard to get a reliable trend out in some cases. This is a comparison of with some observational trends. So this is from a study a few years ago, which looked at computing density trends based on observations. This is the same observational data set in each case, but analyzed in different ways. So the top two panels show linear regression based analyses, and then the bottom one is a machine learning approach, a neural network, to analyze a long-term trend. And they also looked at different periods because of that deep solar minimum around 2008 and 2009. And it looks like, especially the linear regression based analyses struggle a little bit with that deep solar minimum and produce much stronger trends when that period is included, whereas they say the machine learning approach removes that much better, which may be the case. But if we compare the simulated trends based on the linear regression analysis with the linear regression analysis approaches, these are two different background models that are being used, basically. This one being slightly better, then there's a reasonable, it's in the right sort of ballpark what we simulate and what we see in the observations. So it looks like the density trends, the global mean density trends, can be largely explained by the simulation. Then can look a little bit at spatial variations. So this is now again trends in temperature at 400 kilometers calculated with the most advanced linear regression model, and we see even if we do this in different ways and try and get more stable trend out, we always see a stronger cooling here in the northern hemisphere polar region. And based on some earlier work I did with TIE-GCM simulations, I already knew that the CO2 effect, this happens to be at slightly lower altitude and for a different time frame, but the CO2 effect on the temperature in the thermosphere is actually relatively uniform. So you wouldn't really expect this sort of feature to occur here if it was due to just CO2 cooling. And indeed, if we look at the combined CO2 magnetic field effect, then you see this strong cooling feature in the northern hemisphere polar region popping out. So that's quite nice. That seems to roughly match what we see there. And based on the simulation with Wacom-X, we also showed that there was a strong trend in the joule heating in this region, which corresponds more or less with where we see the strong cooling. So it looks like this spatial structure is the result of a change in joule heating, which we can again link to main magnetic field changes occurring. Probably the movement away, the movement of the magnetic pole away from that region results in reduced joule heating. Also look at some of the F2 peak parameters here. So just to remind you, NMF2 is the peak electron density, HMF2 is the height of the peak electron density, and we're looking at those parameters here. These are again the spatial variations in these parameters, and we see the strongest trends occurring in this region. Again, the southern part of the Atlantic Ocean, parts of South America, and parts of Africa there. So exactly in the region where the strongest magnetic field changes occur, which is not surprising, because we know that the magnetic field is important for HMF2 and for NMF2. But for HMF2, we also see in the rest of the world a clear reduction. So, and that is again consistent with CO2-induced cooling and contraction, whereas the NMF2 trends seem to be small outside of the Atlantic sector. There's a little bit of a signal here as well in the Northern Hemisphere auroral zone. That is probably a magnetic field effect. So we can look at, we can try and separate those effects out again. So this is background state, this is HMF2, this is FOF2, this is the CO2 induced change in HMF2 and FOF2, and this is the magnetic field induced change. So you see kind of an average reduction in HMF2 associated with CO2. You see nothing here. That's because I used the same scale for these two plots, and the magnetic field effect is simply much larger than the CO2 effect on FOF2. Oh, and I should have pointed out FOF2 is the critical frequency, which is what you actually measure with ionosondes, but it is directly related to NMF2, so the peak electron density. So the peak electron density is not really affected by CO2 changes, whereas HMF2 is, and both are affected by magnetic field changes. So I've talked a lot about those magnetic field effects, but I've not really explained that much about how it works. So I thought I attempted here to try and capture that in one slide with a bit of an overview. I realized quite quickly that it became rather complicated because there are so many connections, but I'm going to try and talk through this, and hopefully that gives you a sense of how the magnetic field's strength in this case affects the IT system, the ionosphere thermosphere system, and then we'll talk about the effects of magnetic field orientations next as well. So we'll start here. This represents the magnetic field strength, and as you reduce the magnetic field strength, that is going to reduce the size of the magnetosphere. As you see here, this is based on a series of simulations I did, very idealized simulations, in which the magnetic field is varied quite extremely. So these kind of magnetic field changes you would expect perhaps on geological timescales, not really on human timescales, but it is good to kind of get a feel of how magnetic field strength influences various important parameters. So as the magnetosphere is reduced, just because you have a smaller magnetosphere, you have less potential for interaction with the solar wind and the interplanetary magnetic field, and that reduces the cross-polar cap potential. And so that line here is a theoretical relationship that the model simulations kind of confirm, at least if you not go to too extreme cases. So you reduce the cross-polar cap potential. You also, again, purely because of geometric effects, you change the size of the polar cap because you change where the open-closed field line boundary is. But the effect of a smaller magnetosphere, smaller dipole moment, is that you increase the size of the polar cap. And so both of those effects act to reduce the electric field, but also the magnetic field is being reduced. And the high latitude E cross B drifts, they scale as the magnitude of the electric field divided by the magnitude of the magnetic field. And so it depends on the balance between these two, what then happens to the E cross B drifts. So you see that for a magnetic field that is relatively close to our present day magnetic field, a reduction in that field strength would increase the E cross B drift magnitudes. And that can then impact on the neutral winds as well through ion drag, and it impacts on the Joule heating. The neutral winds impact on the Joule heating, but the Joule heating is also affected by the ionospheric conductivity, which is also directly affected by the magnetic field strength. So the weaker the magnetic field, the more freedom the ions and electrons have to move, and so that increases the ionospheric conductivity. And that has obviously consequences for current systems, such as the solar quiet current system at low to mid latitudes. This is an example of the magnetic perturbations associated with that current system that you would expect to see on the ground. So they increase for a reduced dipole moment. Also field line currents change, although they are also impacted, of course, by changes in the magnetosphere, but I thought I would leave that out here just to not overcrowd the whole slide with lots of arrows. And of course the conductivity impacts on the Joule heating. And the Joule heating affects the neutral temperature structure. Neutral winds can also affect the neutral temperature structure, but also changes in neutral temperature can affect the neutral winds. Changes in neutral temperature can affect the electron density. The neutral winds and the E cross B drifts can also affect the electron density. And so there are lots of connections here, and I've probably missed out some of the connections that really exist. But you can see it's a very coupled system. So once you start off changing your magnetosphere, changing the conductivity, you change lots of other things within the IT system that are then impacted by those changes. And for magnetic field orientation, again, there are lots of different pathways by which it can affect the system. So the first one I wanted to talk about is changes in solar wind magnetosphere coupling efficiency. So basically for how efficient the coupling between the solar wind and magnetosphere is, it matters what your orientation of the dipole is. So whether the dipole is oriented towards or away from the sun, or whether it is perpendicular to the sun-earth line, all matters. And so that varies over the course of a year, over the course of a day as well. This is a figure just illustrating the variation of the angle mu between the dipole axis and the GSM-Z axis, and you can see that seasonal and UT variation. And the magnitude of that variation depends on the orientation of the magnetic field. And so differences that you get, for instance, between equinox and solstice depend to a degree on the orientation of the magnetic field. And I explored that some time ago with some very simplified simulations with a coupled magnetosphere, ionosphere, thermosphere model. And so we looked at the reconnection line during equinox on average, and also during solstice, again, a 24-hour average. And you see the color code kind of indicates how much reconnection takes place, if you like. It's the electric field parallel to the reconnection line, and you see that you have much more of that reconnection taking place along a longer stretch of the reconnection line at the nose of the magnetosphere for equinox than you do at solstice. And this is just a different plot, kind of saying the same thing, but also including some results for a purely magnetosphere model. That's the dashed lines, which eliminates the feedback that you get from the ionospheric conductivity. So yeah, and the main result still stands that you know, depending on the season in this case, which is linked in with the orientation of the magnetic field, you get differences in the solar wind magnetosphere coupling efficiency. And that then influences the strength of the high latitude ionospheric convection and the Joule heating, with obvious further knock-on effects. Another thing that's important is that the orientation of the magnetic field affects where key features are in a geographic reference frame. So that's sort of illustrated here as you increase the tilt angle, so the misalignment between the geographic and magnetic poles, or all ovals move to lower latitudes, and you get this more and more of an undulation in the magnetic equator as well. And where your magnetic equator is matters, for instance, for current systems. So I've got an example here from a recent study that I was involved in. This is based on data from Tatuoca Station. I believe that is in Brazil, but at least in the area that is affected by magnetic field changes. And so Tatuoca back in the 1960s was about 1,000 kilometers from the magnetic equator, but by 2015 it was almost on the magnetic equator. And so this is the daily magnetic variation seen in 1961 in the pink and 2015 in the green, which indicates the strength of the currents in the ionosphere. And you see much stronger currents in 2015 than in 1961, and that indicates a switch from the SQ current system towards the equatorial electrojet, which is a very strong current that is very closely bound to the magnetic equator. And that is basically due to the approach of the magnetic equator. And we could reproduce that as well in the TIGCM. So that is just an example of how observations at a specific geographic station could be impacted by long-term changes in the magnetic field. Also for the polar cap, at high latitudes, you have further knock-on effects, if you like, of where exactly those features are located. So this is an example of differences in the two hemispheres, which brings me on to the next topic later on. So we see here the magnetic quasi-dipole grids for the southern hemisphere in the red and the northern hemisphere in the blue, projected onto northern hemisphere geographic coordinates. And that's just to give an indication of how different they are. So you see here also in the gray, the geographic high latitude circle, so this 80-degree circle. You see that there's quite a lot of overlap still with the northern hemisphere magnetic 80-degree circle, but a lot less with the southern hemisphere one, and that's because the offset between the geographic axis and the quasi-dipole axis for the southern hemisphere is larger than for the northern hemisphere, and that has implications for how much solar illumination you get over the polar cap, which is then going to affect how much electron density there is, what the conductivity is, etc. And so, and you get much larger daily variation. That's illustrated here. So this is the difference between the minimum and maximum sunlit fractions in the two hemispheres that you get over the course of a day as a function of days since winter solstice. So you get much more variability in the southern hemisphere than in the northern hemisphere, because you get that greater offset, and yeah, you get that rotation over the course of a day in the southern hemisphere, being much more prominent than in the northern hemisphere. And finally, plasma transport processes are also strongly affected by the orientation of the magnetic field. So obviously E-B drifts are impacted by magnetic field changes, but also plasma transport by neutral winds that blow ionospheric plasma across the magnetic field. The plasma likes to stay on a field line. So if you have, for instance, equatorward winds, as here indicated in the blue, then the plasma motion in the red is going to have an upward component there, and that can influence the electron density structure. As you move plasma up, it moves into a region of less recombination, so you tend to get higher electron densities. If you reverse the neutral winds, then you get a downward component, you get the opposite effect, but also simply how the neutral winds project onto the magnetic field is going to affect these, the exact nature of these plasma transport vectors. Yeah, and plasma diffusion also takes place mainly along the magnetic field. So again, the orientation of the magnetic field is going to have an influence on that. So that gives you a flavor of the various ways in which the magnetic field orientation affects the ionosphere-thermosphere system. And then I wanted to move on to north-south asymmetries briefly. So I talked a little bit about the differences in offset between the geographic and well, different kinds of magnetic poles. You can look at the dip poles where the magnetic field is exactly vertical, or you can look at in this case, it's AACGM coordinates, which is a different kind of magnetic coordinate system that's quite often used. And again, you see a greater offset between the high latitude region here in the southern hemisphere and the geographic high latitude region than you do in the northern hemisphere. And there's also differences in the field strength structure and the overall magnetic field strength. So on the whole, the northern hemisphere magnetic field strength at high latitudes is weaker than in the southern hemisphere. And you also get sort of two centers of relatively stronger magnetic field, whereas you only get one clear center with a very strong magnetic field in the southern hemisphere high latitude region. And also that can have some implications for differences that we might observe between the two hemispheres. So I've looked at that kind of, again, very schematically, just looking at how differences in field strength affect the conductance and the field line currents here. So if you have a weaker magnetic field strength, as in the northern hemisphere, you would expect higher conductivity and larger field line currents. And that happens to be also what observations show. This is a plot from Cnossen et al. Based on Ampere data. From what I understand, the data is being reprocessed now, and this plot might be a little bit out of date, but I don't have a new one yet. But what it shows is that the northern hemisphere field line currents are on average stronger than the southern hemisphere ones. Whether all of this difference can be explained by differences in magnetic field strength is not really clear, but it looks like it could at least play a role in explaining those differences. Together with Matthias Förster, I also looked at high latitude ion drift magnitudes and neutral wind magnitudes. This is the ion drifts based on, I think, pretty much a full solar cycle of cluster data. This is based on CHAMP data, also from quite a few years, though not a full solar cycle. And what we see in the Northern Hemisphere is stronger ion drifts than in the Southern Hemisphere. And we see neutral winds kind of being stronger in local summer, so not really a north-south asymmetry that you can see here. But what we expect from the magnetic field asymmetry is that as you have a weaker magnetic field, you should get stronger E cross B drifts, which is exactly what we see. So that matches. We would, in principle, then also expect the neutral winds in the Northern Hemisphere to be stronger because of ion drag. And while that's not immediately obvious like this, if we plot the observational data in a different way and plot it as a function of days since summer solstice, then you see that at least during local winter, you do get stronger neutral winds in the Northern Hemisphere than in the Southern Hemisphere. And perhaps that makes sense because during local winter, the ion drag effect will be relatively more important because you have less solar illumination. So other forces to do with solar illumination, such as the pressure gradient force, would be less important for the neutral winds. So the fact that this pops out during local winter might make sense. Then one final example of north-south asymmetry is this one, where we looked at the neutral wind variance. So this is not absolute magnitude, but how much it varies in the Northern Hemisphere versus the Southern Hemisphere, based on the greater offset between the geographic and magnetic axes in the Southern Hemisphere. You would expect greater variance in the Southern Hemisphere, which is what you see here. And we can also show that with model simulations where we used a dipolar magnetic field, which produces no significant difference between the two hemispheres. And if we then introduce the full magnetic field strength, you see that popping out with greater variance for the Southern Hemisphere. This is in the Southern Hemisphere, neutral winds, again at high latitudes. And so probably that's related to larger daily variation in solar illumination and a greater mismatch between processes that are being organized in geographic and magnetic coordinates and that are sort of constantly competing with each other and moving the neutral winds in different ways, more so in the Southern Hemisphere than in the Northern Hemisphere. Okay, and then I'm going to come to my last slide with a brief summary. So I've been showing you that the upper atmosphere climate is changing with some important implications for satellite drag and space debris in particular. We need to be quite careful to extract long-term trends from observational data, but also from model data if we do it in a similar way and look at the statistical significance of the trends. And removing solar cycle variations in particular is quite tricky. Then in terms of causes of long-term trends, we have the increase in CO2 concentration, which is really dominant for the thermosphere, especially in terms of the global mean. But Earth magnetic field changes are also important, especially for the ionosphere and especially in the Atlantic sector, although there can be knock-on effects for the thermosphere as well. Any sort of long-term variation in the sun or also in geomagnetic activity, I should have included here, would also introduce a long-term change, but we usually filter those effects out. And then there's a possibility of some indirect dynamical effects that we haven't really got a very good handle on yet. Both the magnetic field strength and orientation affect the ionosphere thermosphere through various coupled pathways. And the same kind of mechanisms can also explain some of the north-south asymmetries that we see in the polar upper atmosphere. Okay, I'm going to stop there and thanks for your attention, and I'll take any questions.
Okay, good. Thank you, Ingrid. Thank you for a very nice seminar. And yeah, I think it has been really excellent. So we have a few questions in the chat already, and this is just a reminder for everyone else. So if you want to ask questions to Ingrid, just please raise your hand or write that in the chat. So the first one is from Wuhu Fen, and he said that I have a question regarding the density trend using 3 different linear regression equations. If we look at the temperature trend, then there are no significant trend in temperature since WACCMX has the constant pressure. Why density trend is more flat, less annual variation, which is different in temperature trends?
Yeah, I think it's because the density trend is kind of affected by everything that goes on below that altitude as well. So whereas the temperature trend is a more localized feature, basically. So you might see differences between the way the temperature trend varies with different end years of the analysis compared to the density trends. I think it is to do with more of an integrated effect for the density trends.
Okay, so there is a question also by Wu Hufeng, and actually there is a reply by David Timms in the chat, but the question is a related question about the regression. Traditionally, each factor used in the regression should be independent. So if you have 2 terms about the F10.7, is it still valid in the regression?
Well, it's my understanding that because the relationship isn't necessarily a purely linear relationship by including those 2 terms, so a linear F10.7 term and a quadratic one, you sort of capture that. So I don't know if that's necessarily a problem. Yeah, I mean, I get the point that they are not completely independent that way, I suppose, because F10.7 goes into both of them.
Yeah, actually, David said, answering to the question, wouldn't that only matter if you care about the relative amplitude of those terms? Correlation across 2 variables shouldn't make the other terms more unstable. So maybe.
Okay, that's a lot of detailed discussion about the methodology. Yeah. Okay, I need to think about that.
Okay. But then there is a comment by John Coxon about I think it's the last part of your talk of the asymmetries. So he said that the data is being reprocessed and Colin Waters indicate that the asymmetries is still in the new data and it should be available soon.
Okay, that's interesting. Yeah. I wonder if it's still the same kind of magnitude or if it's either increased or reduced in the new analysis. But yeah, that's
I think John has the microphone open, so maybe.
So Colin spoke a little bit about it in a RAS-G meeting, which I believe is on YouTube, so I can send you the link to his talk. I got an email last month telling me the Ampere data, the new wave, was available, but they're having problems with the data pipeline, so I still can't actually get any of it. But it's very close, and it's a question I'm going to answer. So I'll send you an email when I start looking at the data.
Okay, yeah, that sounds good.
So yeah, I don't see any other comments in the chat. If anyone else wants to ask anything, you can either write in the chat, raise your hand, open the microphone. Okay, so I only see comments as great talk and thanks, Ingrid. So I think that's all. So I think maybe we can stop in here. Oh, there's a question. Yes, Wuhu.
Ingrid. Yeah, so you are using 1, can you say something about the model? For example, what kind of process are missing, or you think still need to understand for the ionosphere using 1,
So just in general, what is missing in the model? Yeah, so that kind of I sort of mentioned already that we can't really capture gravity wave effects very well yet with the model, and I think that is an important area to make improvements in, especially because some recent work has indicated that there could be secondary gravity waves that are being generated in the upper mesosphere, lower thermosphere region. I think that could have further impacts on the thermosphere ionosphere system, and the current parameterizations that we use don't have that effect included at all. And so, yeah, I think that for me, that would be an important area where improvements could be made.
Okay, thank you.
There is another question by Susan Macmillan. If you had large budget, what in situ measurements would you like to constrain things more?
I don't know. Yeah, I find it difficult. I think what is important for these kind of long-term trend studies is that we keep existing data sets going. You know, for anything long-term, it's not so much about perhaps setting up new observations, although, you know, those have their benefits as well, of course. But for these long-term trends studies, it's really important to just continue monitoring and continue the existing data sets, and don't close down observational facilities that have already produced really long data sets, because they will become only more valuable if you can keep them going.
Well, there are some general comments about how great was your flowchart. Actually, I think it was really, really great. It's a nice summary of all the steps involved in the magnetosphere and ionosphere coupling. And someone also said, "Viva ionosons," which I also agree with that. Anyway, so I think there are no more comments, at least for the talk itself. So I think we can stop in here. I just want to thank you again for the very great seminar that you gave today. And as always, so in a couple of hours, hopefully it will be online in YouTube and I will send an email to the MIST mailing list. And just a reminder, so we don't have a seminar in December, so we are taking a break for Christmas time, but we will resume hopefully in January. So I will just send an email later in time. Okay, so thank you everyone for being here today, and yeah, have a nice holidays and see you soon. Bye.
Okay, bye.